Okay, welcome back everyone. In this video we're going to do a quick practice problem involving Snell's law. And so what we have in this problem is, by the way, this is number 40 on page 726. We have a glass block which is given to us as 10.0 centimeters thick, and it has an index of refraction of 1.65. We are given an incident angle of 40 degrees, and let's zoom in a little bit to see what's really going on here. Basically what happens is that this ray of light, because it's going from I guess N2 would be this material and N1 would be 1 outside, because we're going from less dense to more dense, it's going to bend towards the normal, and then again when it goes from more dense to less dense, it'll bend back out again. Now what I was hoping to show is that the starting ray and ending ray were pretty much parallel. And so what we're trying to find in this problem is the perpendicular distance between the original ray and the refracted ray as it comes out. Okay, so this is going to get a little bit crazy, so I need to draw a slightly different diagram. Again, this is the boundary, okay? This is the normal. This is the ray coming in, and this, wait, hold on a second. This is the refracted ray, okay? This is the continued version, and then here's the other boundary, and it continues like that. So basically what we're trying to find right here is this distance in red, and that makes it a little bit easier. So what we can do is a couple of things. First of all, let's label some things. Let's label this height right here, or distance, as y. Let's label the hypotenuse as d. We know that this is 40 degrees right here. We know that this is going to be theta refracted. And we know that this angle right here is going to be 40 minus theta refracted. Okay, so when we apply Snell's law, we use n1 sine theta 1 equals n2 sine theta 2. So n1 is 1 times the sine of 40 degrees, n2 is 1.65, and then we want the sine of theta 2. Okay, now the way to do this in your calculator is to do the inverse sine. Alright, so we do the sine of 40 degrees over 1.65, and then we have to take the inverse sine of that. That's going to get us theta 2. So if you're not very familiar or comfortable with inverse sine, come talk to me and we can kind of go over how to do this. So this is 22.9 degrees, which means that this teeny tiny little angle right here is about 17.1, if I have my math right. Okay? So now what we have are two right triangles. So let me try to show you those. We have a right triangle right here, okay? That consists of y and the refracted ray. And we have a right triangle right here. Okay, maybe my highlighter is a better choice. Let's get that turquoise highlighter. Okay, I have a right triangle right here, and another right triangle right here. Alright, so basically we are just going to set up a little bit of a ratio, okay? And just for fun, we're going to call the actual length of the refracted ray r. So therefore, we are able to say that the cosine of theta refracted is going to be adjacent, or r, over, let me try that again. It's going to be the adjacent, or y, over the hypotenuse, r. And then also we can write that of 17.1 degrees, so that's this angle right here, is going to be opposite over hypotenuse. Okay, now theta refracted is actually 22.9 degrees. Okay, and those are just numbers that we can calculate. So the point here is that I have a common factor of 1 over r for each one. So this means that the cosine of 22.9 degrees over y is equal to the sine of 17.1 degrees over d. And keep in mind that d is what we're trying to find. Okay? So d ends up basically being the, let's see here. Well, I have to do some cross multiplying. I have to do y times the sine of 17.1 divided by the cosine of 22.9. And remember that y is 0.1 meters. So this gives us a distance of 0.032 meters, or something like 3.2 centimeters. Okay? So that is not too terrible, and we just have to be very careful with our angles with this. Okay, see you next time.